So in this video, what we're going to talk about is the application of the first order differential equations. In particular, what I'm going to explain is about the mixing of solution without reaction, or simply the mixture problem. So for the mixture problem, we commonly have a specific tank with an initial volume and an initial solute. In this tank, there is a solution that is coming in at a certain rate and at a certain concentration. At the same time, there is a solution that is coming out at a certain rate and at a certain concentration as well. Commonly, these problems ask the time to get a certain concentration and the concentration at a certain time. So in order to solve this problem, keep in mind that the input minus the output will give you the abbreviation. For the input, you multiply the rate and the concentration of the solution coming in and subtract it to the rate and the concentration of the solution coming out. For the concentration of the solution coming out, we use this formula. Solute over the initial volume plus the rate of the input minus the rate of the output multiplied to a certain time. So in order for you to determine what method to use in order to solve this problem, consider these two conditions. If the rate of the input is not equal to the rate of the output, what you're going to use is linear differential equation. But if the rate of the input is equal to the rate of the output, what you're going to use is variable separable. So we're going to show you an example of how to solve this kind of problems.
This is an example of solving mixture problems using first-order differential equation.
A large tank is filled to capacity with 500 gallons of pure water. Brine containing 2 pounds of salt per gallon is pumped into the tank at a rate of 5 gallons per minute. The well-mixed solution is pumped out at the same rate. Find the number of pounds of salt in the tank at this time t.
Given R1 is equal to 5 gallons per minute, R2 is also equal to 5 gallons per minute, C1 is equal to 2 pounds per gallon, C2 is equal to Q over V initial plus R1 minus R2 times T, and our V initial is equal to 500 gallons. And now, we are required to find the number of pounds of salt in the tank at the time t. And now, we are required to find the number of pounds of salt in the tank at the time t.
Solution: dq over dt is equal to R1 times C1 minus R2 times C2. R1 times C1 minus R2 times our C2, which was Q over V initial plus R1 minus R2 times our time. Substitute are given. 5 times 2 minus 5 times Q over 500 plus 5 minus 5 minus 5 times T. This will now become dq over dt is equal to 10 minus Q over 100. So dq over dt is equal to 1000 minus Q over 100. We will multiply both sides by dt over 1000 minus Q. And we will get dq over 1000 minus Q is equal to dt over 100. Integrate both sides. This will now become integral of dq over 1000 minus Q is equal to 1 over 100 integral of dt. Let u is equal to 1000 minus Q, and du will now become negative dq. We will get negative ln of 1000 minus Q is equal to T over 100 plus C. Then ln of 1000 minus Q is equal to negative T ln negative T over 100 plus C. Then 1000 minus Q is equal to E to the negative T over 100 times E to the C. By simplifying this, now our Q of T is equal to E to the negative T over 100 times C minus 1000. So our Q of T is equal to E to the negative T over 100 times C minus 1000. At T of Q of 0 is equal to 0, Q of 0 is equal to E to the negative 0 over 100 times C minus 1000. 0 is equal to 1 times C minus 1000. So C will now become 1000.
So the final answer is Q of T is equal to 1000 times E to the negative T over 100 minus 1000.
I'm asked to solve problem 23 under the assumption that the solution is pumped out at a faster rate of 10 gallons per minute. So let's look at problem number 23 again. So a large tank is filled with a filled to capacity of 500 gallons of fresh water. Okay. And we assume that the input rate is equal to 5 gallons per minute. C1 concentration of 2 pounds per gallon. Now, our new assumption is the rate coming out is 10 gallons per minute at constant searing, so the concentration of the volume in the tank is equal to the concentration coming out of the tank. Okay, let's solve this. So solution. The formula for the V2 is equal to V is equal to the initial volume plus R1 minus R2 times time. We need to find the time when the tank's volume is 0. So we let the volume of the tank equals 0. The initial volume is 500 gallons plus R1 is equal to 5 gallons per minute minus 10 gallons per minute times the time. Do this, we can find the time, which is equal to 100 minutes. So at 100 minutes, at the given rates, the tank will be empty.
So for our next topic will be the circuits, which has two scenarios, the RL and the RC circuits. At first, there will be the RL circuits, which involves resistance and inductance. This represents the resistance, and the other one represents the inductance. RL circuits, we are going to get the formula or the equation for the I, which is going to be derived from the formula of the EMF, which is the voltage of the resistance and the voltage of the inductance. In here, we all know that the formula for the voltage of resistance is IR, while for the inductance is the derivative of the current over the derivative of time times the inductance. Given this equation, we can now derive for the first order linear equation of the current. The equation for the derivative of the current over time will be di over dt plus resistance over inductance times the current is equals to the electromotive force over L. For the next scenario will be the RC circuits, which includes the capacitance and the resistance. In RC circuits, we are going to solve for the equation of the charge, which is, again, we are going to get from the electromotive force, E is equals to the voltage of the capacitance plus the voltage of the resistance. The voltage of the capacitance is the charge over the capacitance plus IR, and we all know that I is dq over dt. Substituting the I, we get E is equals to Q over C plus dq over dt times R. Given this equation, we can now derive for the formula of the charge, which is the derivative of the charge over time plus 1 over the resistance times the capacitance times the charge is equals to the electromotive force over the resistance.
So first, let's write the given. Let's draw a circuit. The resistance is measured using a voltmeter for the resistance. And our resistance is 50 ohms. While the electromotive force is 30 volts. And the inductance is also measured by a voltmeter, which measures to be 0.1 Henry.